So there are a couple of sections left in chapter 13, but I don't have a ton of time to go over those, but I just wanted to briefly mention a couple things. And you've probably seen this in a lot more detail than I would cover anyways in a biology course. Osmotic pressure and cells. We're thinking about the cell wall being a semi-permeable membrane, just like a membrane would be with osmotic pressure, so it can let water in and out. There's different terms associated with what a cell will look like when it's in a hypertonic or a hypotonic environment. Another section that shows up in chapter 13 is about colloids. So colloids are a type of solution, but they're not truly a solution because they have large particles dispersed throughout them. And they scatter light in what we call the Tyndall effect. So you've probably seen these types of solutions before. I mean, you've certainly seen fog. And so that's a type of colloidal solution where you have droplets of water dispersed in a gas. We have emulsions as well, and then sols are like a solid particle dispersed in a liquid. I don't know if anyone has done any work with nanoparticles. The other way you can make a sol is if you take powdered non-dairy creamer and you put it in water and you shake it up just a little bit of it, it makes a cloudy solution. That's a sol as well. You can use it to scatter light. Micelles also show up, so micelles are kind of neat. They have it's basically a collection of molecules that are surrounding, well, depending on the type of micelle, could be surrounding a hydrophobic solution or mixture or liquid. Let me get my highlighter here. So a micelle is formed when you have a long chain hydrocarbon with a polar end. So this is a polar end, and this is a nonpolar chain. A bunch of these sort of form together, and this is how detergents work. So stearate, if you read your detergent labels, there's stearates in detergents. We have a nonpolar end that will enter into an oil droplet, and a polar end around the outside of that. That polar end can dissolve in water, and this will allow small particles of oil to be dissolved into an aqueous solution. Okay. That's really all the time I want to spend on these topics, but it doesn't mean they aren't important. So make sure you read through these sections. You may see a question or two on the exam about this. All right. So we're going to start chapter 14. Changing gears here a little bit. We're going to talk about chemical kinetics. I think this is wrong. I think your book now only goes up to section 14.6. Either way, we're covering the whole chapter here. Our first sections here are just a little bit of a background on what kinetics are, and then how we can think about how concentrations change during the course of a reaction. So one thing I want to point out is the term spontaneous and fast. We're going to come back to the term spontaneous in a lot more detail when we get to chapter 19. I believe I mentioned Gibbs free energy. We were talking about entropy, and that's related to the term spontaneous. So a reaction may be spontaneous, meaning it'll just happen on its own. You don't have to put energy into it. But that doesn't mean it occurs quickly. So for instance, the reaction of nitrogen gas combining with hydrogen gas and forming ammonia is a spontaneous reaction. They've changed my app. But it doesn't occur quickly at 1 atmosphere. What in the world? So, for instance, nitrogen and hydrogen can be found in the atmosphere, but we don't really have ammonia in any large quantity in our atmosphere. And that's because, despite the fact that these components are in the mixture, that is air, they don't react very quickly, at least at 25 Celsius in 1 atmosphere. Now, you may have heard of the Haber-Bosch process. I think this is how you spell Bosch. So in the Haber-Bosch process, it's a way of making this ammonia formation reaction occur quickly at 1 atmosphere at relatively low pressures, and it involves the use of a catalyst. So a catalyst makes a reaction occur more quickly. We're going to talk more about those. It makes it so the reaction occurs efficiently and more quickly. So it uses a catalyst. What do you all know about ammonia? How is it used? Was that used for cleaning? What else? Without this reaction, without the Haber-Bosch process, none of us would probably be here. It is the reason why there's almost 8 billion people on Earth. The formation of ammonia, ammonia is used in fertilizer, which is how we feed 8 billion people. Without fertilizer, we wouldn't be able to make enough food, enough crops to survive. Now, I do want to say one other thing about Haber, because I think this is an important thing. His goal was not to create fertilizer. His goal was to create weapons of war, chemical gases used in World War I, and which he was very good at. And he has won a Nobel Prize for the ammonia reaction, but he also is responsible, given his inventions, for killing lots and lots of people. So I want to just say, Haber has done some good things and also some things that make him a war criminal. He actually has a very interesting story, so good read on the Wikipedia page there if you're interested. Okay, but spice does not mean fast. So what do when we're thinking about kinetics, we're thinking about the rates of reactions. We're also thinking about the steps that are involved in a reaction. And so with that, we're going to learn about reaction mechanisms. Mechanisms mean what has to form in order for the next step of a reaction to take place. Usually we don't just have, we see reactants and products, and oftentimes there's intermediate stages that we don't always write out. There's a whole lot of work being done in chemical fields, looking at kinetics, looking at reaction mechanisms and things like that. Okay, so in order for, I want you to think about this. Okay, in order for a reaction to occur, molecules have to collide, right? And if you recall your study of gases, I believe it was chapter 10 in your book, Kinetic Molecular Theory of Gases, you have to have molecules collide for a reaction to occur in the gas phase. They have to be oriented a certain way, and things like this, right? You guys, does that sound somewhat familiar? Okay. So given that knowledge, take a look at these 5 different factors and think about how the reaction rate is going to be affected, which one occurs faster. So take a look there and we'll go over this. Okay, so what about the concentration of reactants, excuse me. Which will occur faster, a high concentration or a low concentration? High, yep. Higher concentration of reactants, more chance for those reactants to collide and then go on to react. Temperature, high or low? High? Why is that? More energy, stronger collisions. Molecules moving around faster. Physical state, solid, liquid, or gas? Gas. I'm going to circle liquid and gas. So in a gas, particles could be very far apart, right? And that may make a reaction occur less quickly than if those same things were in a solution. Right? So we'll circle both of those. They're about the same, and there's different factors, and you just know that the sol is the slowest, I guess. Particle size, large particles or small particles? Large? Small? Small particles tend to react more quickly. This is a little harder to think about. It is possible to have a reaction occur where everything is in the solid phase. And you can do this, we used to do an experiment like this in Gen Chem, where you would take some metal salts, grind them together, and then react them at high temperature. No solutions formed at all. But the small particles has extra surface area, more contact, allows the reaction to occur more quickly.
Smaller particles are less inertia.
Small particles what?
Have less inertia.
Less inertia. Oh, so we're thinking solid phase, I guess. So in that case, it's not going to play a role. There was another question, I think. Pretty good. Did you have your hand raised? Okay, sorry. Okay, and then this one's just a statement. A catalyst is going to increase the rate of the reaction. Okay. Like I said, we're going to talk more about catalysts. Okay, so quick ABC choices here. For which of the following vessels will the reaction occur the quickest or the fastest? Assume that all are at the same temperature. Yeah. B. Why is that?
They're closer together than they are in C.
Yep.
And they're still-
Yep. In B, the reaction will occur the fastest. We have particles in the gas phase. They're going to occur more quickly than those in the solid phase. And comparing B and C, there's a greater concentration in B, and so the reactants have a better chance of colliding with each other. Cool. Okay, so let's sort of take this up a notch here in terms of difficulty, I think. Thinking about reaction rates and how concentrations change during the course of a reaction. So we have a plot here that has concentration of reactant on the y-axis and time on the x-axis. This reactant is known as chlorobutane. If you're interested. It's reacting with water to form butanol and hydrochloric acid. So another thing I want to point out here with this plot, and I think maybe you've seen this, maybe not, I can't remember. Whenever we put a reactant or a product in brackets, that means concentration of. So brackets mean concentration. So on our x-axis, we have chlorobutane in brackets, so that's concentration of chlorobutane. So given the way this plot looks, what's happening to the concentration of chlorobutane as the reaction proceeds? It's decreasing, right? Yeah, so it's decreasing over time. Okay, so here we have just over a course of 900 seconds, a way of looking at the concentration. What else can we tell about the rate during the course of the reaction given this plot? Yeah?
Starts faster and time goes on and slows down.
Yeah, so it starts out at some sort of rate, and then it decreases as time goes on. Now, why might that be? Yeah. There's less of that reactant, and so the reaction rate decreases. Okay? So we have a reactant, all reactant in the vessel, initially, no product. We allow it to react, the concentration of reactant decreases, the concentration of product is going to increase. Eventually, the concentration of reactant is getting low relative to where it was, and so there are less collisions, and so that rate decreases. Okay? As we will see in the next chapter, we're going to get to a place called equilibrium, a point called equilibrium, where a reaction is occurring in the forward direction and the reverse direction at the same rate. But for now, we're just going to mainly be looking at, before we get to points of equilibrium. Okay, so a steeper slope corresponds to the faster rate. You want to do some calculus? Fans of calculus can find that. Okay, so now here we have a graph of concentration of a substance over time. Take a look at our choices here, A, B, C, and D, and decide which of these is represented in the plot. Okay, so is X a reactant or a product? Product? Why do we know that? Yeah, the concentration starts probably at 0. There's no units and no numbers on here, but let's say it's 0, or very low at least. And then what about the rate? Is it speeding up or slowing down? It's slowing down. So the answer is D. Okay. We know that the rate is slowing down because our plot tends to sort of flatten out. Okay. Everyone okay on that? Okay. In line. Okay. So we can think about rate in a couple of ways. We can think about an average rate, and we can think about an instantaneous rate. Okay. So a good analogy here is driving in your car. Right? I'm from Youngstown. I think I mentioned that probably the first lecture. It's about 150 miles from here. Right? It takes me about 3 hours to get there if I drive. And so that would be an average rate of about 15 miles an hour. Right? However, we know that I'm not going 50 miles an hour the whole way there. I started out in Columbus. I'm on city streets. Can't go higher than 25 or 35 miles an hour. I get on the highway. I'm going the speed limit, of course, 70. And then, get back into town, things slow down, things like that. Okay? So the average rate would be the distance that I traveled over the total time it takes. So the 150 miles in 3 hours. The instantaneous rate is whenever I look at my speedometer and I see how fast I'm going, that's the instantaneous rate. Okay? So we will typically be thinking about instantaneous rates for a reaction, not average rates. But I do want you to point out that those are different terms, okay? Now, we can look at a rate over a given amount of time. So that's what's being shown in this equation. So this is our chlorobutane reaction again. So again, 1 chlorobutane plus 1 water forms butanol and hydrochloric acid. If we want to think about how the rate is changing over time for the concentration of chlorobutane, what we're really doing is looking at the change in concentration over time, and over the change in time. And we know that we know that the concentration is decreasing, so we put a negative sign in front of that. Now we typically give rates, we report them as positive values. So the negative sign here makes that a positive value overall. So if we're decreasing, the change in concentration is going to be a negative value. So we put the negative in front to make it a positive value. Okay? So let me write this out. So what we're going to see here is the change in concentration. I'm just going to use x for the sake of space. At some time 2 minus the change in concentration at some time 1. So, or we could do a final concentration minus initial, same thing, 2 minus 1, 1 F minus 1, or I, excuse me, over, oops, I don't need deltas here, sorry. Okay, over T2 minus T1. Yes?
We're doing instantaneous rate of change. Are we going to be doing derivatives in this class?
We are not going to be doing derivatives. Yes, no calculus needed. We can all breathe a sigh of relief, including me. I'm pretty rusty. We have a question in the back. Yeah. Hold on, everyone. So we put a negative sign in for a reactant when the concentration is decreasing. So anytime we have a reactant, we're going to have a negative sign in front of it, right? You notice on this side, this is the concentration of product, and we don't have a negative sign here. We set these equal to each other, and that has to do with the stoichiometry of the reaction. So for every 1 chlorobutane that reacts, we form 1 butanol. So the rate of depletion of the reactant is equal to the rate of formation of the product. If we were to draw that, we'll just put concentration here, time here. We're going to have our reactant going away and our product increasing, and the rates would be the same. This is going to be dependent, though, on the stoichiometry. Okay, so that's 1 to 1, so that's why the rates are the same. Now the difference is the sign, right? So again, decreasing and increasing. This is the slope of the tangent. Yes. They are not inversely proportional. They are equal. If the stoichiometry is 1 to 1, they are equal except for the sign. Yeah. The sign is reversed. So if we want to do a more general equation, we can do that. Probably a good idea. Okay. So if we have A plus B reacting to form C plus D, we can set up a rate expression that's going to look something like this. So negative 1 over a, that's the stoichiometric coefficient, lowercase a, change in the concentration over change in time, etc. There's a question.
Oh, yeah, so when you write the reactants, are you always gonna write that as negative?
Yeah, in this type of expression, you're always going to write that as a negative sign. If you're relating it to a product, especially. Now, I will say the rates are always given as positive values. So you may see a problem where it says the rate at which the reactant is reacting is 5 moles per liter per second. You have to know that that means it's decreasing. Because we just report rates as negative values, or as positive values. But if you wanted to then take that rate and compare it to a product, you want to put a negative sign in front of it. Okay. Everyone comfortable with this equation? This wise. Okay, so let's take a look then. We're gonna finish early today. I'll slow down. Okay, we're gonna let's look at a reaction here where we have 2 HI, hydroiodic acid, forming hydrogen and iodine. So take a look at the stoichiometry. We have 2 of the reactant, 1 in front of the products, each of the products. And our problem here says that at a certain point in time, H2 gas is being produced at a rate of 3 moles per liter per second. At what rate is the iodine gas being produced? Here's an equation. So this is adapted just from that AA, B plus BB thing. So I did, take a look at this. Okay. This is, y'all are going to forget to do this. That stoichiometric coefficient, 1 over it. Okay? For a reactant, minus. So minus 1/2 change in the reactant concentration over change in time equals the change in a product over change in time. And there's a 1 over 1 here too. We just don't see it because it's 1. Right? Okay, so let's work on this problem. At what rate is I2 being produced? Yeah.
At 3.0 moles per second.
Yeah, at 3.0 moles per liter per second. Yeah, so those units are capital M over S, which is moles per liter times seconds. Those are pretty typical units for our rates when we're working with aqueous solutions especially. And you can tell that the rates are going to be the same. Take a look at our plot here. We have concentration on Y, time on X. And we've essentially drawn one line for both the formation of H2 and the formation of I2. Okay? We can do that because their stoichiometric coefficients are the same. That's what's dictating the rate of the reaction in this case. Okay, so then at what rate is HI being consumed? Now, you might need to do some math here. Take your time and do that one real quick. Not that quick. Write it out. Maybe write it out. What did y'all get? Yep. But question. I will. Yeah, for sure. All right, let's do that. so we were told that H2 gas is being produced at a rate of 3 moles per liter per second. And so that says that this is equal to 3 moles per liter per second. So delta H2 over delta T equals 3 moles per liter per second, right? So the rate at a given time, for that same time period now, I guess that has to, we should specify that. So at what rate is HI being consumed for that same given time period that we're looking with H2? I mean, there's not really any other options for doing the math. And so what we really want to solve for is delta HI over delta T. We know this is equal to 3.0. We're going to multiply both sides by 2 over 1. And we'll end up with 6 moles per liter per second. And I have a minus sign because it's decreasing. You look confused? I'm not going to call you out. Sorry, I called you out. But you do. I don't know what that.
No, I don't get it.
Okay.
Good. I think that was.
You're confused?
Yeah.
Okay, great. So we have, how can I help? Tell me how you're confused. Okay. Yeah. Okay, yeah. So I'll walk you through it one more time. So we know that the rate of H2 is being produced at 3 moles per liter per second. We can relate the formation of that product to the depletion of the reactant using this equation. Okay? We can ignore the other product. We don't need to worry about that. And so if we write that out, we know that this is equal to 3.0. Multiply both sides of the equation by 2 over 1. And then we can solve for the rate of change of the concentration of HI. And there's a minus. Oh, I forgot the minus in that line. Well, yeah, so that's minus, and then I moved it over. Either way. Yeah.
So,
Wait, 1 second. Yep.
did you just flip it 1/2 and make it positive, or like is that all good? Where does the 2 come from?
The 2 is coming from here. Yeah, so I multiplied both sides by 2 over 1. Sorry, 2 over 1 to cancel this out. And then was that your same question or?
Like multiplying by the reciprocal, but leaving this.
Yeah, I just left the sign there. That's probably it. You can do what you want with this sign, and again, keep in mind we typically report rates as positive values, but we know that if a rate if it's for a reactant, it's decreasing. Okay, that's just something to keep in mind. Sign convention. Yes. You just do stoichiometry. Yes, absolutely. Yep. It's all based on the stoichiometry for this type of rate reaction. If you know the rate and it's asking you to relate the reactant rate and the product's rate, and you know one of them, this is the way to go. Now we're going to do a few other types of rate problems, and they're going to be a little bit more difficult than this. But this is for when you know the rate of a reactant or a product. Yeah?
So when it says that, like, the question is how the rate of H2, would you answer it as a negative? Or?
I probably would put it as a positive value. And I hope that that's what is true for everyone. Because, I mean, the book specifically says it. I read it today. We report these as positive values. I'll fight for you if that's not the case. You can do it the way we've done. Okay. Let's do another one real quick. I think this is basically the last sort of, we have some summaries after this, but this is going to kind of get us to the end of the section 14.2. So here we have a reaction of NO2 gas forming 2NO and O2. And we are given concentration of NO at 2 different times. And given this data, we're going to answer these 2 questions. So over this time period, what is the rate of appearance of O2? That's the first one. And then over that same time period, what is the rate of disappearance of NO2? And to help out, I'll put this. You will not be given this equation, I'll tell you that. You all right? Just the building falling apart, it's fine. Fun story. I was here as a grad student when this room got remodeled, and the seats used to be a lot more comfortable than they are. And when everyone realized how narrow these seats were, people were furious. And it was like no one wanted to have any seminars in this room, and it was just a disaster. But now it's falling apart, so maybe we'll get it remodeled again. This is pretty nice and round. Okay. You guys feel comfortable starting these problems? Was it a resounding Okay. So for this problem, we only know things about concentration of NO, right? But we know the stoichiometry for the reaction, which is good. We can relate that stoichiometry with the other reactants and products, so that's good. So if we're thinking about the rate of appearance of O2, so that's a product. We have information on another product. And so we can say that, and I'm taking the stoichiometry, 1/2 change in concentration of NO over change in time is equal to, again, stoichiometry, 1/1, delta change in O2 concentration over change in time. Yes?
Why is it not negative 1/2 like it was in the example?
Yeah, why is it not negative? Yeah.
Because this is a product, not a reactant.
Exactly. Both are products, right? So the rate, the sign of the rate is going to be the same for both of these. Great. So now we can take, I'm going to move this down here a little bit. Next line. We can take our given information. So again, 1/2. I'm going to do concentration at time 2.0061 minus 0.0055. This is going to be moles per liter. And then the time, make sure you, make sure you keep these in order, right? If you use the second one as time 2, you got to use the second in the denominator. Does that make sense? Everyone okay with this? Okay. real easy to forget to multiply by 1/2 here, because I definitely did that in my notes when I was working this out before class. But our rate that I get, so change in the concentration of O2 over change in time is equal to 4.3 times 10 to the minus 6 moles per liter per second. Did anyone work it out and get that? Okay.
Yeah.
Cool. Good. Okay. Questions on that? And what about the rate of disappearance of NO2? Okay. Again, we can set up our equation. Now we have 1 over 2, 1/2 1/2 the change in concentration of NO2 over change in time. And there's a minus sign in front of that because it's a reactant. Equals 1 over 2 times the change in concentration of NO over change in time. Okay, so you use the same data, right? We know change in NO over change in time is equal to all of this. We have this 1/2 unit, or 1/2 factor in front of each of these fractions. One of them is negative because of the reactant. But we can essentially get rid of that. So the change in the concentration of NO2 with the minus sign in front of it is equal to this, which was 8.6 times 10 to the minus 6 moles per liter per second. I can't erase that anymore. I'm not intending to circle the 1/2. That 1/2 did. Does that make sense? I didn't do all of it out. Sorry about that. Does that make sense? Yes.
So is there a specific reason why you use the NO on the right side of that equation? If it's like the question is.
Yeah, so the reason I used NO is just because that's the information we were given in the table. You could, because we knew the rate of appearance of O2 from the previous question, you could have used that rate as well. Yeah. Yes?
Do we not put in the negative because it's disappearance? Or?
Yeah, so because the question said what is the rate of disappearance, I just left it as a positive value for rate. Yes?
So we have to multiply the first O2 times 2 to get it because geometry.
Yes, you could do it that way. Yeah, so when we calculated this value, this is just this times 2. Yeah. Yep, exactly. Other questions? These are good. Yes. Why I subtracted these? Okay, so the question is, why did I subtract the 0.0061 from the 0.0055? So I take the rate at the later time, the 285 seconds, and subtract it from, let's do this one. Yeah, take the rate at the later time and subtract it from the later, the early time. That's just based on the definition of the change. Now, if you mess that up in your math and you realize you do that, you just change the sign. Anything else? Picture here. Yeah. Okay. So just to sort of summarize what we've done here. Reaction rates, usually given in units of moles per liter per second. Keep an eye on those units. For most reactions, the rate slows down as the reaction proceeds. Again, we're losing a concentration of reactants. Here's the term instantaneous rate. If we were to find that, and let me go back to the previous. Rates can be written in terms of the appearance of products or the disappearance of reactants, but you have to watch that stoichiometry and recall, that relationship. Okay, so when we start thinking about chapter 15, which is far away, not that far, but it is, we need to remember that these reactions are going to be reversible, and they have equilibria. So when we start forming products, those products actually start reforming reactants. Let's see. And so when we put, for instance, from this last problem, NO2 in a container, that forward reaction happens. Eventually enough product builds up that the reverse reaction starts occurring, and then eventually we get equal rates, forward reaction and reverse reaction, and that is equilibrium. But again, another chapter. Next time, we'll start we'll be on 14, section 3. We're all good on